An automated weather station is an integrated system of components that are used to measure, record, and often transmit weather parameters such as temperature, wind speed and direction, solar radiation, and precipitation. Weather stations are used on land and sea for a variety of operational and research purposes. We study weather because we want to know how it will impact our daily lives. The principal parameters in relation to weather and climate are air temperature, air pressure, humidity, clouds, their existence, types, precipitation like snow, snow hail, etc., visibility, wind and solar radiation. These parameters are the basis of meteorological observation. The study of these parameters helps in real-time preparation of weather analysis, forecasts and severe weather warnings, study of climate, local weather-dependent operations, for example, local aerodrome flying operations, construction work on land and at sea, hydrology and agricultural meteorology, and research in meteorology and climatology. We know that it is through our senses we interact with the world around us. But certainly, our senses are not good enough at quantifying these weather parameters more accurately. Hence, the invention of manual measurement of these weather parameters came into the picture. But down the line, with the advancement in the science and technology, automated version of these instruments are outracing its conventional counterpart and now is in huge demand. So, let us see what automation will provide that the manual observation doesn't. The automated system will evaluate and report only weather that has passed through sampling volume of sensor array. Observer visualizes general atmospheric conditions prevailing at the time of record and makes certain assessments on the state. Well-maintained and calibrated AWS provides accurate data. Manual errors and bias may in fact affect the data quality. Automated AWS works round the clock, irrespective of sun and rain. Data collection manually in nights and during bad weather conditions may lead to breaks. Real-time data acquisition, which is the ultimate aim, could be achieved in AWS. Accuracy is dependent on observers' knowledge and perception. Initial costs are high in AWS, but requires very less maintenance, less security threats to the system, and tampering possibility, which are more subjective, regular monitoring of the system. As per WMO, a meteorological station at which observations are made and transmitted automatically is known as Automatic Weather Station or AWS. Depending on the data observation on AWS is broadly categorized into real-time AWS and offline AWS. A real-time AWS provides data to users of meteorological observations in real time, typically at program times. Real-time use of an AWS is the provision of synoptic data and the monitoring of critical warning states such as storms and river or tide levels, and offline AWS records data on site on internal or external data storage devices, possibly combined with the display of actual data. Now let us understand the hardware requirements of an AWS. Generally, it has three main parts. A standard observing area, preferably no smaller than 25 meters by 25 meters, where a series of automated sensors sited at the recommended positions and interconnected to one or more data collection units using interfaces. A CPU for sensor data acquisition and conversion into a computer-readable format. Proper processing of data by means of a microprocessor-based system in accordance with specified algorithms. The temporary storage of processed data and their transmission to remote users of meteorological information and peripheral equipment, such as a stabilized power supply providing power to the various parts of the station, a real-time clock, and built-in test equipment for automatic monitoring. AWS mast plays a crucial role for data observation. Now, depending upon the application, the height of mast is chosen. For example, for data modeling, aviation, for stratified distances, the height of the mast is 30 meters. For hydrological purpose, the height would be 10 meters, and for agricultural purpose, it would be 3 meters. So what makes AWS more lucrative than its conventional counterpart are its smart sensors. These sensors are robust, almost maintenance-free, and has sensors with an electrical output. Depending on their output and the characteristics, the sensors can be classified as analog, digital, and intelligent sensors. So in analog sensors, the output is commonly in the form of voltage, current charge, resistance, or capacitance. Signal conditioning converts these basic signals into voltage signals. In digital sensors, the digital signal has information in the form of bit or group of bits and sensors with pulse or frequency output. In intelligent sensors or transducers, the sensors have a microprocessor performing basic data acquisition, including processing functions and providing an output in serial digital or parallel form. Rainfall intensity. The first and foremost parameter that will be discussed is rainfall intensity. Tipping bucket rainfall, TBR gauges are widely used for measuring this parameter. In TBR bucket, on one raised end of tipper is positioned directly beneath the collector spout, collecting the water first. Seesaw tips when bucket collects equivalent of 0.1 mm of rainfall. Each tip empties one side of seesaw and positions other bucket under the funnel. During the tipping process, a magnet moves past a sensor, a reed switch, and signals that it has accumulated one count, say 0.1 mm. After each tip, measured water is funneled out from bottom of gauge. Some basic precautions should be taken during the measurement, like You should avoid inaccurate rainfall readings by checking the rain collector funnel often for obstructions like dirt and debris. Remove the rain collector and check underneath as well. Dust and debris can also affect the operation of a TBR, and clean the buckets and collector funnel gently using water and mild liquid detergent, and then rinse it thoroughly. The second important parameter to be measured is temperature. The temperature sensor employs the fact that the electrical resistance of resistor elements changes as a function of temperature. As it is possible to record the temperature digitally, there is no need to have special devices to determine temperature maxima and minima, since it is easy to record the data at small time steps over the whole day and then use the software to search the database for local maxima and minima. Now let us understand the sources of errors and how to troubleshoot while measuring any parameters. Like the electrical thermometers usually have a short time constant, and when sampled by fast electronic circuits, their output reflects high frequency, low amplitude fluctuations of the local temperature. This can be avoided by using sensors with a long time constant by artificially damping the response with a suitable circuit to increase the time constant of the output signal. Secondly, the proper protection of the sensor against the effects of radiation is of great concern. For accurate measurements, the radiation shields should be artificially ventilated with an airspeed of about 3 meters per second. But precautions should be taken to prevent the entry of aerosols and drizzle in order to avoid wet bulb effects. In AWS, barometric pressures are measured by pressure sensors. In this, tiny silicon diaphragms are attached to a capacitance gauge which bends to different degrees depending on the external pressure, altering the capacitance of the attached capacitor. Data from these instruments can be easily recorded digitally, allowing high time resolution studies of pressure wave events in the atmosphere. As far as humidity sensor is concerned, it uses a capacitor which consists of two metal plates separated by a thin polymer film. The film absorbs or exudes water vapor as the humidity increases or decreases, thus changing the dielectric constant of the film. This in turn changes the capacitance of the unit, which can be recorded electronically. The capacitance can then be converted to a measure of humidity using suitable conversion formulae. These instruments are very portable and can be calibrated to quite high accuracy. The use of conventional cup or propeller anemometers with pulse or frequency output is widespread and presents no particular technical problem other than that associated with icing in severe conditions for wind speed measurement. This complication can be overcome by heating the sensor in moderate icing conditions. But This results in a significant increase in electrical power consumption. So, it is recommended that for a new cup and the propeller anemometers, the response length should be smaller than 5 meters. Nowadays, ultrasonic anemometers are becoming popular because they don't have any moving parts. They measure wind speed based on the time of flight of sonic pulses between pairs of transducers. Measurements from pairs of transducers can be combined to yield a measurement of velocity in 1, 2, or 3-dimensional flow. The spatial resolution is given by the path length between transducers, which is typically 10 to 20 centimeters. Ultrasonic anemometers can take measurements with very fine temporal resolution, 20 Hz or better, which makes them well suited for turbulence measurements. The lack of moving parts makes them appropriate for long-term use. For wind direction measurements, wind vanes are used. As vane turns, it rotates a stainless steel shaft held in place with instrument-grade bearings. A waterproof conductive plastic potentiometer is coupled to base of shaft. This potentiometer has excellent linearity. Very low torque is required to move wiper. Electronic switching inside signal conditioning module provides an output range of 0 to 359 degrees. Pyranometers are used to measure the solar radiation. It is a radiometer used to measure all radiation incidents on its flat receiver from a 2-pi steradians hemisphere. A pyranometer converts the global solar radiation it receives into an electrical signal that can be measured. Pyranometers measure a portion of the solar spectrum. It uses a series of thermoelectric junctions to provide a signal of several microvolt per watt per meter square, proportional to the temperature difference between a black absorbing surface and a reference. Let us see the possible sources of errors attached with pyranometers. The main technical problem is that these sensors are usually analog devices that produce very small and continuously variable voltages as signal output. These voltages are very vulnerable to electromagnetic interference on the signal cables, and adequate measurements have to be taken. The problem of contamination of the front aperture is severe for radiation measurements. The dust deposits on uncleaned pyranometer domes are considered to give 2% loss of accuracy. Now, let us focus on sighting of AWS sensors on AWS mast. The international standard height for measurements of air temperature is at 1250 millimeters, 4 feet above the ground. Temperature can vary by a surprisingly large amount with height above ground under certain weather conditions. Humidity sensor is usually mounted alongside temperature sensor in most AWS systems and does not have independent sighting criteria. The wind speed and the direction are dramatically affected near the ground level by all physical obstructions. Even in a flat, unobstructed location, wind speed is markedly reduced close to ground level by frictional effect of ground surface. For these reasons, official sensor height for recording wind speed is 10 meters above ground level in a clear, unobstructed location. Rain rarely falls vertically, but is usually blown to a greater or lesser degree in wind. For consistent and accurate measurements, it is therefore important that rain gauge is located in open area, say a large lawn or ground, where nearby objects such as buildings, walls and trees won't deflect entry of wind-blown rain into the gauge. The rain gauge should be positioned at a distance corresponding to 2 to 4 times the height of any nearby obstruction. Gauges should be positioned about 1.5 meter above the ground in a flat area away from any obstructions such as fences which might cause air turbulence and consequent non-uniform deposition of rain droplets. The barometric pressure does not vary across local area at uniform altitude. So, the pressure is measured by sensor inside AWS console and not by external sensor. At the end, it is concluded that the observer should have fair idea on the method of data observations, citing criteria, and the sources of error attached with each sensor and its troubleshooting. Then only the sole aim of accurate data measurement will be possible from AWS.